Okay, so in this problem, we're presented with a very weird game. So a man pays $1, and he can win his dollar back. He can lose it. He can make $2. He can make $4. He can make $8. He can make any large amount of money if he gets lucky enough. So let's run down, according to the rules, the probabilities of each of these. And we're going to ignore the $1 price for now, because we'll simply subtract $1 from the expected value at the end, instead of making the calculations more annoying. So, right off the bat, we're just keeping track of the total, the expected value for the total paid out, and then we'll subtract 1. So there's a 1 in 2 chance that the first flip is a tails. In that case, the total is $0. Okay. Since this is 0, we don't need to add anything to the expected value. Now there's a 1 in 4 chance that the first flip is a heads, and the second flip is a tails. In which case, the running total will end up being $1. Therefore, we want to add 1/4, the probability, times $1, the amount, to get $1/4, or I'll write 25 cents, of expected value. And so we're going to add this to our expected value total, and then we'll total it up at the end. Okay, what about 1/8? We're going to keep going. This is when you get heads, tails. The machine pays out $2. And in terms of expected value, we multiply $2 by 1/8. And again, strangely, we get 25 cents. Okay, let's keep going, a couple more. What about 1 in 16? Heads, tails. Well, this will pay out $4. And again, if we multiply $4 by a 1 in 16 chance, we get 25 cents. Well, this seems really odd. And we could keep going. We could see 1 in 32 for heads, tails. $8, 25 cents, because we're taking 8 over 32. So this is going to keep going forever, right? We can see from this logic that this pattern is not going to stop. Every time the amount doubles and the probability halves, so every time we're adding the same amount to the total. So our expected value is going to keep increasing. We're going to keep adding 1/4 to our expected value. Now, what does this mean in practice? Well, first of all, it means that our expected value is going to quickly dwarf this $1, so it's going to become insignificant. And really, our expected value is going to be something akin to infinity, right? Because we're just going to keep adding 1/4. And this seems like a really weird idea, because obviously you can't win infinity dollars. Every game is going to give you some amount of money, and most of the time it's going to give you, $0 or $1, or you're going to lose your dollar half the time. What this means is that if you play this game enough, if you play it over a large amount of time, like 1,000,000 times, you'll win a lot of money. And if you play it 1,000,000,000 times, you'll win a lot more money per game on average than if you play 1,000,000 times. So the average amount of money per game is only going to increase on average as you increase the number of games played. This is similar to if we had, say, an expected value of 10, we would expect the expected value or the average value per game played to get closer to 10 as the number of games played gets closer. Here, we're getting closer to infinity, which just means larger. Closer to infinity always means larger. So as we play more and more games, our average value per game is just going to increase and increase and increase.